This afternoon. So what I will do is continue and finish off what I was going to say about tabular. And what I'll do is I'll go through the syntax in more detail and then explain a couple of the kind of novel constructs in tabular. And then I will get into Fabula, which was irresistible because we decided we wanted to look at the R programming language, and we sort of figured, we've been looking at these new research-oriented probabilistic programming languages, and we realized that people in the R community had been using these formulas, they call them, for describing linear regressions, very sophisticated linear regressions for some time. And so we did a bit of semantic detective work to understand how that language works. It's very compact and really rather popular. And so to do that, we came up with something called the Regression Calculus, which is a fun bit of type theory that I will go through. And then that has led to Fabula, which is like the Regression Calculus meets tabular. And we also started to look at adding these formulas to Stan, which is like I mentioned, is a pretty popular probabilistic programming language. So then I will finish the afternoon by talking about the semantics of Stan. So we did a paper at Popl about that this January, and I will go through the details of that. And the punchline is that surprisingly, this probabilistic programming language is actually deterministic. So I'll get to that in an hour or so. Right, so back to tabular. Let me go through the syntax of what is the language. And so I talked about, I jokingly call them the big four probabilistic programming languages: Bugs, Infer.net, Church, and Stan. And all of them kind of look like imperative languages, or with the exception of of Church, which is more like a scheme, a sort of Lisp-like language. The thing that's unique about tabular is that it's based on a database schema. So in fact, the syntax starts with a database schema. So a schema, and we saw lots of examples yesterday, a schema is a series of tables, and each table has a name. So in the TrueSkill example, the two tables are the players and the matches, and then each of them has got a capital T table model. And a table model is a sequence of column descriptors. So little c is the name of the column, and tie is the name of the type. And then the column types look like that. So there's scalar types. Mod n is every number up to n minus 0 up to n minus 1. Real is I can't help resist. So mod, I never mentioned this to Nick, but we stole mod n from F star. It seems a very nice name for the type of numbers up to n minus 1. You'll hear about that tomorrow, everyone, when Nick talks about F star. And we have arrays, sized arrays. So the type system actually of tabular is, to an extent, is a dependently typed system because we track the sizes of tables and references to them. But it's not particularly difficult to do that. I won't go into the details of that. So so there we are. So this is just a table, a sort of regular database schema. If we do this, we turn it into tabular. So what we add in tabular is that every column has got a label descriptor and an A. Well, what are these guys? Well, L is the level. And this indicates, like I said yesterday, so it's static versus implicitly sort of per instance. So this says whether the column is really just a single value, which is generally a latent variable, like say the mean or the standard deviation of a Gaussian, say in linear regression, or it might be dynamic. And then the annotation we put is one of these three forms. It's an input, it's latent or output. And if it's latent or output, then we have a probabilistic expression on it. So some columns are just inputs. So we have no model for them. So examples would be in the players column, in the matches column of TrueSkill, there's two columns for player 1 and player 2, which just say who played who else. And we're not trying to give a probabilistic model of the players. You want a probabilistic model if you want to be able to predict them if they're missing. And in this situation, I'm assuming we always know the players, and I don't want to predict them. So they're just inputs. And then if you want to do a latent column, you just say latent and give give a probabilistic model. Otherwise, it's an output, and you give a probabilistic model. This is the syntax for probabilistic models. The simplest thing is like a distribution, like D might be Gaussian with a mean and a variance. We have a bunch of deterministic functions F, which includes plus and minus and various other operations. We've got conditionals I'm not put in there. This expression is a way of referring to a component of another table. So in the true skill example, when we figure out the performance of an individual in a particular match, we take their name, their identity, and dereference it to get the latent skill in the other table. So we do that with the dot notation, so C, and this C is just a constant. What is the difference between a latent and output, you might ask? So a latent means that it's not actually physically present. This column is not physically present in the database, so essentially we're adding it. Output means it is actually physically present in the database, and if the column, but the column is sort of nullable in the sense that we allow missing items in some of the rows, and those missing items will be predicted by the model. Okay. Right. Okay, I've just got. What about the semantics? I am going to do the semantics by translation to a conventional, one of the big four probabilistic programming languages. So this could be like Bugs or Stan. And so I hope this, oh darn it, I hope this is reasonably readable. Yes, someone pointed out the colors aren't ideal. I'm sorry about that. So here we are back with true skill. Remember we have our players table and our matches table. So what does this mean as a model? Well, I'm writing out here that you can read this as saying for each row R of players, we compute a new latent skill that is drawn from a Gaussian. So the table becomes a for loop. In fact, all tables become for loops, in effect, just iterating over the rows. And then over here, the matches table is a for loop, and the body of the for loop has an action for each of these guys. So inputs are really just assignments. In this case, player one is just assigned by going r.player1, and so it's looking up. Each row R of matches. So player one is a local variable. It's a local copy of player one. Same for player two, and then we actually have some random variables. Perf1 and perf2 are drawn from these Gaussians with their parameters given by these deterministic expressions. Then win1 is computed just as this Boolean, and then we have a test implicitly where we test whether the column of match outcomes, whether the item in that column is absent or not. So if it's not present, if it's not null, we do nothing at this point. But if it is actually present, then we do conditioning, and we condition that the predicted output win1 is actually the same as r.win1. So this is, if you remember in my first slide in the lecture yesterday, I said that probabilistic programming languages have a construct for randomness, which is exemplified here by, say, Gaussian, and have a construct for indicating conditioning, which is applying a constraint to the world. And here I'm using an observe statement, which is, has equivalents in things like Bugs or Stan. And we observe this particular test. So this is expressing, conditioning of the model. I was discussing with Marco, and the Sam Staten is giving a course about the semantics, the sort of foundational semantics of probabilistic programming languages, and he will be explaining in detail how constructs like observe are given a semantics using measure theory. I will just assume that this is possible, and I'm not going to go into the details of how you do it. So that's basically the semantics of Tabula by translation to a simpler sort of, if you like, standard probabilistic programming language. Okay, is that reasonably clear? Any questions?
You had all those annotations. Is there any way we could contact those?
Well, in a sense, they are. I've not given a detailed sort of blow-by-blow semantics of how they all get interpreted, but this is the effect of it, where the latent variables become these new random variables. And then this output variable is not a new random variable, but is actually just conditioning on the output of this particular model.
And in your
4 columns.
That's syntax protocol.
Oh, yes, that's right. In the schema, that's right. There's only 4 components in the schema. Where, yes, exactly. Yeah. Will.
So how would you model interactions between players? Like if you wanted to say, they have some skill independently, but these two people players together, like player 1 might have less skill against player 2 because he doesn't like player 2 or something. Like, is it possible to introduce arbitrary factors like that for pairwise relationships between people?
Yes, it is. I don't have details here on any slide, but there's this system called TrueSkill 2 that is, and there's a recent paper about that, and that's a rather more sophisticated model than this, and it models interactions between team players. So it's about like teams of players in multiplayer games interacting, and the model of the performance of the team is like a sort of a combination of the individual performances. So yeah, you can be very creative in the kind of modeling that you do. Okay, let me move on. To talk about just a few more constructs of the language. So let me say a bit about actually using it to make decisions. So I've got one slide about like Bayesian decision making in tabular, and this introduces the concept that that we've got multiple sort of levels in play in a tabular model. So one level is just concrete given data, like the columns of player 1 and player 2. Another level is the level of sort of modeled or random data, which is things like win1, which is like the outcome of a Gaussian distribution. Yes, well, the output of a probabilistic expression. Right here, I've squished this model down into a one-liner where the performances are inlined into that cell. So that's 2 levels. And the third one is a sort of post-processing level that, having done inference, maybe you want to do some work. Maybe you want to decide bets that you're going to place or not. So this model is explaining that. So players and matches are just the same as in TrueSkill that we've seen so far. But in addition, I've now got a table called bets. So these are bets that I've been offered. So I'm sorry this is rather small. But, well, there it is. So this... Can I do anything about that? I'm not sure if I can, unfortunately. Right. So you can't really see this, it's rather too small, sorry about that. But we've got a table of bets where we've got a match and odds. And we've got, on match 2, the odds are, here's a bet with odds 4-1. And for match 2 also, there's a bet for 2-1. And this actually is, this matches column, it's the same one as I had yesterday, where we've got Alice loses to Bob, and then Bob loses to Cynthia, and then the match hasn't happened yet, is Alice playing Cynthia. And you might think Alice is probably going to lose again, because Cynthia seems to be the strongest of the 3. And you've been given some odds about the bets that you might get. So 4-1 would mean that you put your say, dollar on the table, and if they win, you get $4 back. If you lose your dollar. So you've got to make a decision. Am I going to place this bet or not? And if I don't place the bet, I keep my dollar. So I'm sort of, let's say I'm 1 up. On the other hand, if I place the bet, then I may or may not get the 4 or might get nothing. So what should I do? So what I'm showing here is how we can use tabular, this kind of post-processing level, to do computations based on the inferred probabilities. So in particular, what this table here is doing is that for every bet, it first of all works out the probability, according to the model, of whether the player is going to win, whether the bet would succeed. And we do that with this syntax here, which is a bit of a mouthful, I'm afraid, but we say infer dot, and we give the type of the distribution that we're expecting and the bias from it. So this stuff here is basically just saying, give me the probability from the Bernoulli distribution that's inferred for match.win1. And then here I calculate my expected utility. So the idea here is, there's sort of 2 possibilities. I'm sort of just weighing up the, which one is going to give the more utility. So I compare them, and then I compare them by doing a subtraction. So one decision would be I place the bet, in which case I'm going to get back P times the odds. The other decision I make is I'm not going to place the bet, in which case with the sort of inverse of the probability, I will keep the money. So that's the expected utility, and then I ask whether that's actually positive, and then I just get Tabula to compute this. And so the way this works behind the scenes is it builds the models I showed you in the semantics, evaluates it, which gives me my probabilities, and then I have this post-processing phase where I do these calculations, and you'll see down here, it basically figures out that it's worth taking the first bet at 4-1, but it's not actually worth taking the second bet. Okay? So it's showing that we're not. So the end game isn't simply getting the probabilities, but actually what you really want to do is take some actions based on the probabilities. Okay. So let me see. Let me move on and explain some of more of the constructs that we invented to sort of reduce the size to capture common patterns in probabilistic models. Okay, so going back, that's the core syntax you've seen, but we're going to extend it with these model expressions. So beforehand, when I gave you the syntax, these annotations had simple probabilistic expressions in them, so you could have latent E or output E. What I'm doing here is enriching it with function calls, and so M it could be an E as before, so anything that was valid before is still valid, but in addition, we have function calls, and we have these index expressions. And they are, let me see, so these function applications are really just a standard, well, more or less standard sort of functions. The twist is that they need to be able to construct values at the different levels in the model. And so that makes them a little subtle to get right. But the idea is to capture common patterns, and I'll give you an example in a moment. So they're functions that take expressions as arguments, and then they build a bit of model. And then this guy here is a way of taking a model and then giving it, sort of replicating it based on some sort of categorical variable. So in my example, well, let me just go into the example, and I think it'll be clearer. So here's the example. So we have this famous data set from the Old Faithful geyser in, I think, Yellowstone National Park. That's it there. And someone has got a data set of times of eruptions, and what they have. And for each eruption, there are two values. There's the duration of the eruption, like in that point there on the left, it took maybe 1.5 minutes, and there's the waiting time since the previous eruption. So in this case, it was 50 minutes. And if you can visually, you can look at that, and you can see that there's two clear clusters with sort of shorter duration eruptions with shorter waiting times, and then longer duration eruptions with longer waiting times. So it's a sort of classic example of doing clustering, which is, that clustering is a machine learning problem of given a data set like that, sort of automatically identifying clusters in the model. And one nice way to do clustering is using a Bayesian model, where you have a sort of cluster variable, a tag, on each row that is learnt from the data. So I can write that in Tabula like this. So here's my faithful table. So eruption duration and waiting time are actual concrete columns that are reals, the data you've seen there. And we add this cluster that's a mod 2, so it's either a 0 or a 1. So it's latent, so it's not physically present, but it's a new sort of latent variable in the table. And we give it this discrete distribution, which is basically equivalent to a fair coin. So a discrete distribution has just got two components, and they've got half each. The prior on this is that they've got, the prior is that it's just fair, it's unknown which of the two clusters that we're part of. And then what we want to do is, we want to get an assignment, which we're going to do by using this inference mechanism. But the interesting part is, how do we actually use the data to decide whether we're in one cluster or another? And the idea is that we're going to have, we're going to fit two Gaussian models to the data, and they're going to be indexed by the cluster variable. So this, you can see here, this expression has really got two things. First of all, it's a function call. So I'm introducing two ideas here, function calls and indexing. And this expression, one moment, is indicating a function call to a function called CG that is going to define the parameters for a Gaussian model together with the output function. And then this part here, the square brackets cluster, is going to index that model by clustering. And what indexing means is that we basically make multiple copies of the parameters, one parameter for each of the scalar index. In this case, there are two indexes, so we've got basically one pair of parameters for that cluster and another pair of parameters for that cluster. That's the intuition. There was a question.
Oh, so can't you just like draw, like, so the 0.5 probabilities, they're hard-coded, right?
Yes.
Can't you like put like a prior on top of that, like the Bayesian distribution?
You could. I've got a, this is a simple example. I'll show you much more complicated things later on. But yeah, this is a nice simple thing. Now what I want to do is explain how the function call mechanism and the indexing mechanism work as a bit of PL. Okay, so it's functional programming. So we decided we could reuse the table syntax that we already have and make it generic and make use of these input columns as sort of inputs to the function. So here is this is like a table that is really like a function. So we have static inputs. So these are, so static meaning there's only one occurrence of them. So these are what they call hyperparameters, in that they are numbers that configure parameters, hence hyperparameter. So we've got the mean of mean and prec of min that are reals, and they have some default values. And then we've got a mean and precision parameter, and they're given these distributions, which depend upon the arguments. And then the actual output, CG, so in this case, this output is going to be replicated for each of the rows in the Old Faithful table, is a Gaussian with the mean and precision given by these parameters. So that's defining a function. And then if we had a simplified version of the call I showed you, we'd just be saying the eruption duration is CG with no arguments. And so we just have a simple defaulting here that if you give no arguments, you get these numbers as sort of reasonable defaults. But if you wish, you can make the arguments explicit. So this just unfolds to that, where we basically take the table, and then any arguments get substituted. And if there are no arguments, then we just substitute in the defaults that are given here, and then we make a copy of this part of the table. And in the paper, we've got full kind of sort of inference rules that explain how to sort of do this very formally, but I think you can see the basic idea by example here, that this constructs a bit of table. So that's the first idea. Then the second idea is index models, and this is really this is a very interesting, widely spread concept in Bayesian modeling. There's a question?
You said in the paper. Which paper was that?
Which paper is? We have a great question. We did a paper at ESOP in. I'm thinking about maybe 2015, 2016. We have two papers about tabular. But what I should say is we have got a sort of final version, a sort of journal article about tabular that I will put in the Slack. And I would love people's feedback, because we're about to finish or submit it, or send the camera-ready copy. So even if you just look at the first few pages, if anything's unclear, let me know, and I'll try and put that on Slack later today. So thanks. Okay, index models. So this is the syntax. We have a model, and we want to make from that a new model whose parameters consist of an array of copies of the parameters of M with size many. So in our example, size is 2. So in my example, I'm going to have 2 copies of the parameters, and then the way that So a model has got parameters, and it's got sort of outputs and latents, etc. Those columns that are sort of per instance of a table. And each of those may make reference to a parameter. And what happens is that the the parameter that is used for any particular row is selected by the e-index, which is an expression that can be evaluated in each row. And in my example, it is the current cluster. So, for example, we've got a cluster in every row. Duration call of the CG function with cluster less than 2, and then that, elaborates to this. So what has happened? So cluster is still there. In the indexed model CG, it has a couple of parameters, mean and prec, and they now become arrays. So 2 parameters for each of them. And so instead of just a single expression, say Gaussian, to define one of these, they become an array comprehension, computing an array of these guys. And then the output, modeling the eruption duration, now is a Gaussian as before, but instead of the mean being just the single parameter, it's the mean of the array. It's the entry in the mean array corresponding to the current cluster, and the same for the precision. Okay? Yes?
What is the difference between the latent variable and the parameter?
Generally, a parameter is like static or once off per table, whereas a latent variable is per row. But formally, in the language, there's no difference. Very good question. Param. I'm sorry. I forgot to say, param is shorthand for static latent. So I should have said that. That wasn't at all clear. Yeah, good question. Thanks. Okay. So yes. So someone was asking, yes, about complexity or can you do more stuff? So this, I just want to give one example of a complicated model that we built. So this is inspired by, in fact, Fabula was inspired by some work that went on in our lab by Samir Singh and Tora Grapel some years ago, where they had this great idea. They wanted to automatically synthesize probabilistic models from the schema of databases, right? But without any user intervention. And so they had an example here of a recommender system where you've got a table of ratings, rather you've got 3 tables. You've got a table of users with some demographics like gender and age. You've got a table of movies with demographics like genre, well, not demographics, are facts about the movie like genre and year. And you've got a table of ratings where each rating is about a movie by a user, and you've got a score out of 5, say. And they said, someone's gone to a lot of trouble to construct this database. Maybe we can generate a probabilistic model that can infer properties from it. And so they said, let's do this. And they came up with this very fancy table thing. I remember Samir was an intern, and he spent days in Visio or something constructing this really fancy model. And it worked. He went and implemented it in infer.net. And put it up proudly, but nobody could really understand it. In fact, I remember Tora and Samir used to have these bitter arguments about, what this notation actually means. You've got this square here, and it was kind of ambiguous. So this seemed like a great sort of PL challenge. Can we come up with a syntax that would allow us to construct these things? And what are the moving parts here? What are the basic concepts? And that really led to the design of Tabular. And in order to capture this, we really need these index models. So I'll show you how we do it. So the users table has got a latent variable. So basically, it's a generalization of the clustering model. I give a very simple clustering model where there's 2 clusters. So here's a more sophisticated one where you've got, here we've got, say, 4 clusters. And we got a function, and I won't elaborate it, called CDiscrete. Actually, CDiscrete does do what you were asking about, in that it has a discrete generator, but it has a parameter that is this generalization of beta called the Dirichlet distribution. So we can we got a function that just constructs a sort of standard model for this cluster, and then for the gender and age. So gender is Boolean. That seems kind of 1995, doesn't it? But anyway, there you are. This is how it is modeled in this particular table. We've got a bool against gender, and it's defined just as C Bernoulli and indexed by user cluster. And in fact, in Tabular, because we can type check user cluster and know that identifier is actually of type mod 4, we don't need to explicitly put in the less than 4. It can just be inserted. And then you have for age, I think we had, why is that discrete n equals 4? I think we had clumped the ages into different brackets by decade, because otherwise it was going to be, there was data. See discrete on the movie cluster, and again, the models of the movie are given by indexed versions of standard models. In this case, they are discrete distributions. And then finally, the ratings model is given here, where we've actually got double clustering. So the ratings model, we don't model user ID and movie ID, so we're not trying to predict them. We won't, if they're missing, we'll be in trouble. But we the score, and so it's out of 5, so we model it with the C discrete n equals 5, and then we doubly index this by the user cluster and the movie cluster. So intuitively what it's doing is, for every rating, it's sort of boiling down the user and the movie to the cluster they belong to, or actually the distribution. It doesn't know, it's not one cluster, it's actually distribution over clusters that it's part of, and then using those probabilistic the scores that the thing is going to give. So that was in a way for Tabula, that was getting back to basics, the original motivation of the language. Here's a slide. Sarah.
In the previous slide, why don't you need to specify the size expression when you're doing model indexing?
Why do I not need to?
Yeah, I thought the syntax previously named was.
Yes, that's what I was saying. That we can actually. Because the language is typed, we can figure out what the type of the index like movie cluster is, and its type is one of these mod types, and so we can get the upper bound from the mod type. Good question.
Sorry, but it says int, so it says mod. Is it actually mod 4 rather than int?
These guys, it's the.
As in, like, movie cluster is C discrete.
You are right. This isn't type correct. This should really be mod 4, which comes from saying n equals 4. So yes, well spotted. Thank you. Okay. I've got a list here of key features. I won't linger on these. I've been saying already that, the key thing is that it's, I guess it's the first language that's kind of based on the schema of the data that we're modeling. Okay, and there's various papers about it. And I have this slide as well, just coming back to the starting point about language-based statistical thinking, about this aspiration to try to build tools that can be usable by a broad set of people. I don't think we're there yet. I think probabilistic programming in languages like Tabula and other languages are making progress, but we still have some way to go. Some specific research challenges is better model suggestion. That was, we in a way we invented Tabula not with the intention that people were going to write it directly, but more to have a compact syntax that we could use in order to synthesize models. And I still think, we haven't done so much on that recently, but I still think that would be a fruitful direction to go, of actually figuring out such models. And I know that, so I had a visit from a student from MIT who works with Vikash Mansinka, and he was very interested in Tabula because he's also thinking about automatically generating models. So I think that work is going on, if not literally in the context of Tabula. Better inference, I've had some fun talking with some of the students from Franklin Wood who are here somewhere about some of the stuff that his team is doing on probabilistic languages and using deep learning to speed up inference in various ways. I think that is a very interesting direction, not so much on the language design level, but on the inference level. So that's pretty cool. What I want to do now is move over to Fabula, which I've been looking forward to. So we've got about 15 minutes to get through this. That might be a challenge. Let's see how we go. So I think I've already set this up, that there are that R is really widely used, and they have this lovely compact notation for defining regressions. And this talk, or this bit of work, which is also at Popple, was about understanding the sort of what that language was, understanding its semantics, and then thinking about how we could extend tabular and stan with that language. And so this slide here is kind of just introducing the notation I will use. So this is like a functional notation for defining models. We call this fun. This was originally it was based on F#. It's very much, I guess it's a bit like Church, but more in a sort of ML style syntax. It's probably similar to the kind of notation that Sam Staten will use in his talks. And I think you can probably get it. I've been talking a lot about this this sort of, if you like, univariate linear regression, where you're trying to predict y given x. And in the model, you've got two parameters, alpha and beta. And alpha is the intercept on the y-axis, and beta is the slope of the line. And so we're trying to fit alpha and beta to the data. And we also have a bit of noise. And so we write that in the language by saying that we have alpha and beta are drawn from these distributions, where these constants I'm not going to go into are just giving sort of large standard deviations. So it's trying to give a sort of what's called a non-informative prior that will be fit by the data. And then pi is used as the variance, if you like, of the noise. So the noise is down here, is a Gaussian with mean 0 and with this sort of large variance that is given by this parameter here. I'm not going to go into detail what the gamma distribution is. Suffice to say, it's a distribution over positive numbers, but let me not go into the details of it. The only gamma distributions we'll ever see is gamma 1 lambda small, which is basically a very, very uncertain number that could be very big, and hence it will get determined by the data. And so this form here is basically defining what the model outputs, which is the two parameters alpha and beta. So it's a pair. We always return a couple of, the coefficients alpha and beta, and then this is an array. And it's over, in this case, the x and y are related to students, so it's an array over some number of students. And in each case, given the x of z, we multiply that by the slope, add in the intercept, and then add a bit of noise. Okay? So it's similar to the models we've seen in Tabular, but it's done in a more kind of, functional notation. And so we've done all this work in probabilistic programming, and I discovered, wow, these R guys, that is for ages, and they write models like that. They just, instead of all that gunk, they just say y twiddles 1 plus x. And I was a bit sort of bummed, thinking they've really kind of, compressed, what it is they're trying to say. And then even worse, I discovered that the +1 is like optional. So you can just say y twiddles x. So it just seemed like we're throwing down the gauntlet. Can we figure out what this language, what this notation means? So that was our plan, to embrace and extend R's formulas to get more succinct probabilistic programs. So that leads to our regression calculus. So we, our challenge is to be able to write down programs that look like this. Y twiddles R, where y is some sort of output, and R is a regression that is defined in terms of input variables. And in general, in a multivariate regressions, you'll have multiple columns, and the y sort of revalued R might be determined by some number of inputs, not just a single x, but x1, x2, x3, and so forth. So we have this grammar here that I am for a regression, and these are defined in terms of predictors. And I think the best way to explain this is by example. So that's what I'll do. I'll just point out, though, at this point, that the new things that we've added are this form here and this form here. This one is a bit of a technicality. This is restriction. It is kind of a refugee from the pi calculus that turns out to be kind of useful for dealing with regressions. But more importantly, this guy here is a way of attaching a regression to the parameters that are used in a predictor in one of these regressions. And this is actually something that's not possible to do in R. So I was a little bit disingenuous when I said that these guys in R have been doing all this before with this very compact notation. They had not been doing Bayesian modeling with these notations. They'd be doing sort of, if you like, sort of classical regressions that don't keep track of uncertainty. And so the point of probabilistic programming is to be Bayesian and to keep track of the uncertainty about your model, and even after you've done you've fit it to some data so that you know how uncertain or not you are, say, about a skill. So in order to do that properly, we need to extend the syntax of regressions with this form. Here's the data set I will use. we've got two tables. This is a kind of a school tests example where the scenario is that you've got a child who's out of school and they do a test in, I don't know, French at the start of the year, and they get a score out of 100, and then they're tested again at the end of the year to see whether their attainment is going up. And so the data set you've got is a whole bunch of test results. So X is before and Y is after, so generally it's bigger. And then we're also tagged with the schools. So this is like data from a school district. This is a classic data set from the sort of Bayesian modeling community from a book by Gelman and Hill. And so you've got X and Y, and then they're also tagged with the school they're on. And then we also have a table here of the average income in the different school of the parents or the different schools. And so we want to bring that into the model as well, just to sort of, so that the model can kind of tease apart the different effects that may be going on. And so then here's the data that I plotted, where I've just color-coded the different schools. And you're seeing, this is actually a synthetic data. So yes, what I've plotted here is a synthetic data set corresponding to this classic schema, and you see that the kids at basically the richer school are sort of doing a bit better than the ones at the other schools. Okay, so then and then formally speaking, I have got a sort of type environment where I'm going to keep track of the types of the different columns. So I'm going to model this data set as 3 columns. U is the array of salaries or average salaries for each of the schools. So anything underlined is the number of entries in that table. And then S is the student. So that's an array, one for each student, of a number that is mod school. So basically an index into this U table. And then X is an array of students' test results. And Y is not given here because it's the thing that's being computed. Okay, so what I'm going to do is just build up a regression model from the piece by piece, and getting more and more sophisticated and sort of better able to fit the data. So the first thing you might say is, let's just have just a pure intercept. So the model looks like that, and we can write this in the calculus like this. So we say that Y is Y twiddles the regression 1, which is which is represent 1 is going to be the syntax of representing a constant, which would be like a constant intercept. And then it has a parameter, which is like where it is on the y-axis. And this syntax here is putting a distribution, a prior, on that parameter. And so we actually have a type-directed translation from the regression calculus into the probabilistic program that corresponds to the linear regression. So in this case, we get the parameter is defined, and we get this regression here that exports the alpha parameter together with the array of predictions for the students. And this is a terrible model, but it is at least very simple. Okay, and we have some syntax sugar. So if we can just omit this Gaussian model if we just want it to be an uninformative prior. So that's quite handy. And in fact, if we don't even want to give the name of the parameter, if we're not referring to it otherwise, and you don't want to actually give it a name, then we can use this restriction operator, which, as I say, is from the pi calculus. But it just basically kind of removes removes references or stops exporting a particular parameter. It doesn't remove the parameter from the model, but it just doesn't export it. Okay, which means that we can get down to this syntax. Then pure noise, we have this form query, and it just becomes this. So it introduces a parameter for the variance of the noise, and then it actually doesn't export it, and then it has this model, this array comprehension for producing basically noise that may or may not fit the data, and it doesn't do a very good job, but that's a basic thing. And then we can combine them. So we have a plus operator that just takes two regressions and adds them together. And so what it does is it basically combines together the declarations of the parameters. So the alpha comes from the left-hand side, the pi comes from the right-hand side, and then in here we just add together the alpha that comes from this model and the Gaussian noise that comes from that model. Okay? intercept with noise, and that's going to do a better job of fitting the data. But what you really want is to get back to where we started, is this sort of this simple univariate linear regression with both a intercept and a slope. And so that becomes this. So we're just adding together 3 different models. And so we combine together the parameters, export alpha and beta, and then inside the for loop, we just add together the intercept, the slope times the actual value of x for that particular student z, and the Gaussian noise. And then and so finally we've got, with our various bits of syntactic sugar, we finally got back to where R started. We can say, we can interpret what y twiddles 1 plus x means. And then so far we've not taken into account that there are multiple schools. We've not used that data at all, but you might well think that would be interesting to see whether there are different sort of baselines for children depending on their parental income. And so that's where this power operator comes from. But really, this is the same as the indexing that you've seen in tabular. So this was a thing so the penny dropped. The kind of indexing that Tora and Samir had been using, to come up with this, implicitly in their heads to construct these complicated sort of indexed models in that Visio picture. That same concept over in the world of R had been used to build these complicated regression models. So this PAR-S, so this is a simpler model, but one per school. And so what it looks like is this. It's like 4 different intercepts that you're going to try and use to fit the data. And so what that becomes is that the PAR-S, so just like in tabular, the effect of PAR, it was like, it was square brackets in but the effect is that it turns the parameter on its left into arrays of parameters. So previously I had a single parameter alpha, but now I've got an array of parameters, one for each of the schools, and it leaves the pi for the noise untouched, and then, where does the noise come? I think that might be a mistake. Oh, yes, it's implicit, yes. The plus query is sort of, implicit. We have to modify the lookup so that the alpha instead of saying alpha previously, we have to change the way we access it because it's now an array. And so we use Z to find the school that we're in and then use that as the index into alpha. And then you might think that well, actually we've shown this, that there is a separate intercept for each school as a function of the income. And now we get to be hierarchical. So this is where it really gets powerful in Bayesian model. So hierarchical model is a regression in which the parameters, the regression coefficients, are themselves given a probability model. And here our calculus becomes recursive, where we really actually put an interesting hierarchical model on the parameters. So there's really 2 regressions going on now. This inner level, we have got a regression R alpha for each of the parameters of the schools that isn't predicting any known data. What it's doing is it's predicting if you like, the imaginary parameters that themselves predict known data. And so that's what I'm showing here, where the regression on these parameters is given the parental income. It predicts the alpha, which is what is it? It's the intercept of these lines here. Okay, so that's corresponding to this part of the model. And then, as before, we have we index per school. And so then this becomes this thing, and at this point maybe you start to give up reading it, but what you can see is the array down here for the regression model up there, and then a separate array down here that is predicting the used in this model. Okay, so what have we got to? We had this regression calculus. There were 2 forms of it. There was these predictors that were constants or variables, or something called interactions, where they actually multiply together U and V, and I haven't illustrated that. And then we have these regressions here. And if you remember, yesterday I was using tabular and I was using this log evidence as a measure of how well the model fits. So I've done the same thing here. So the higher numbers mean a better fit. So I had 6 examples, and you'll find that pure intercept just fails. It just can't fit. There's no variability in it. So infer.net fails to fit. Pure noise is pretty bad. And then as you add more terms into the model, you get better and better. You get a better and better fit. So that's the regression calculus, and I can't resist. I just okay. Just give me a few minutes, and maybe for those of you who are not into type system and rules, you can maybe look away at this point. But I will now just quickly show you the type system for the regression calculus. So we've got predictors that are this form, where there's a predictor produces a t in terms of a typing environment, like the one I showed you for the columns in the data set. And what's this evec? Well, what we have to do here is think about predictors as being cubes, i.e. multidimensional arrays, or in fact tensors of values. So what you've seen, so if it's 0-dimensional, it's a simple constant, like just a single alpha. 1-dimensional, you've seen where you're predicting, say, an array of parameters, and you also get 2-dimensional. And I've never seen really 3-dimensional in any examples. And so we need to give a type to that. So we have a cube expression with dimension evec. And evec is just a list of natural numbers for the size of each of the dimensions. And as I say, n is 0, 2. And so it's a multidimensional array of some type t. And the t is actually generally a real. And then an index for such a cube expression is a list of numbers such that these numbers are actually fall within the bounds. So these here are the bounds, and these indexes are up to those bounds. So the typing rules for the predictors are with respect to the cube, because if you've got a predictor that's sort of nested within a regression, because it's come underneath it may have come underneath this indexing operator, it may actually be generating a cube. So you need to know what the dimension of the cube is. So we have that in this environment here. But the rules are actually pretty simple. That if you've got a scalar, then it's just of type real. If it's a variable, then the variable that you're referring to had better be in one of these cubes, and it better match the dimension that we're dealing with at present. And then an interaction, as I say, is where you multiply together u and v. They'd better both be reals and well typed. And then the translation is as follows. Oh heavens, I suppose it isn't type directed. This part isn't type directed, but it is at least type preserving. So we've got these 3 categories, and a scalar just becomes a scalar. An x is really a cube, and so this translation here takes the indexes into the cube as an argument, and so you get back x of evec, and then the interaction becomes this multiplication. And this statement basically says if you start out well typed and your arguments are well typed, then your translation is also well typed. And then typing rules for regressions are like this. We say a regression exports pi, and so pi is like a list of parameters with their types that are being defined. And so you see that here, for example, that in the typing rule for the coefficient form that introduces the parameter alpha, then it exports a parameter of type real. And the regression is, again, typed in the context of this effec, and that is the dimension of the parameters that are being defined. And so that's on the left here, and it means that you get out an array or a cube of reals indexed by effec. All right, and so then we also have evec, which is the cube of predictions that are being made. So remember, a regression does 2 things. You've seen all the examples. On the left, we had parameters that were being produced, and on the right, we had the array of sort of predictions of y that were being produced. And basically, effec is the dimension of the cube of parameters that are being produced, and evec is the dimension of the cube of predictions that are produced. So for example, if you've got a noise term, it's exporting no parameters, and I don't know, if you add together two regressions, they'd better be both well typed. And here for indexing, I guess this is where the magic happens, that you have V had better be a predictor that produces an index, and the F, the size of it, gets added to the context for the body of the regression, and that's it. So with these typing rules, and then this, which is the translation, which I'm not going to go through in detail. That's why I spent a lot of time going through all the examples. So all the examples have I think everything here has been illustrated by example already, and it's type preserving. So that's good. All right, I will not go into Fabula in detail because I will make these slides available. I'm going to give you a few minutes break. I'll be back at 5 past, and then I will finish by telling you about Stan. Okay. And what I didn't say was we put them into tabular. We got Fabula, but we also did an initial experiment by turning them into regression formulas to add to Stan, because it's a popular language, yeah. So you might wonder, but what is Stan like? So let me go through that. So here is the syntax of a simple model in Stan, similar to ones we've looked at, where you've got a couple of parameters with distributions, and we've got a program. Y is probably a vector, and in Stan, it's a vectorized notation, so you can just say y twiddles normal mu sigma, and it's saying that every entry in the vector is predicted by this guy. And then you have some sort of observation that maybe we happen to know y is 2.1, and so the observation leads to inference, which is expensive. So far I've been talking about Infer.net, which is based on deterministic message passing. Stan, on the other hand, is all based on sampling, and is slower but more accurate than Infer.net in general. Here's a bit of an advert. Go to mcstan.org. It's a very popular language. They've got, well, here's the big numbers of downloads. A lot of people come to their conferences, which is great. It's fast and unusual syntax. So what I showed, so this is the actual syntax that you need to write down, and it has multiple compartments. And actually, as we started to look at Stan, we realized that there were some parallels between how, the compartments in Stan and the different kind of attributes that we had in tabular programs. So up here, they've got a compartment where they say there are n data items, and you've got an array of them. And you've got a couple of parameters, and then here's a model where those statements we saw live. And then there's some generated quantities that are calculated about parameters in the model after they've been discovered. So you maybe want to deterministically compute the variance from the sigma. So we looked at that, and we had two goals. We wanted to understand the principles behind the efficient inference and to make Stan more compositional. We wanted to be able to add functions to Stan, just as we'd had functions in tabular. And I don't think I will not go through how we actually achieved that second part of adding functions. It's in the paper. But what I would like to do in the next 10 minutes is just explain what the semantics of Stan is, and how, surprisingly to me, it's actually deterministic. So this is the part I think, have time to talk through, giving a semantics for Stan based on actually a standard big step operational semantics. And I will introduce these gadgets here. But let me just go through that. Okay, so here is the Stan program we're dealing with. And here is here's some notation for the actual data. So let's say that curly D is a structure that has got, or it's a store actually, that has got 2 in the variable n, and then this array in variable y. These parameters are going to be labeled, we're going to refer to as theta. And we can think about the model block here as a way of generating theta and d, and then we have some other variables. And then let's focus on this model block here. And you would think, And in fact, I think we're encouraged to think about these as being probabilistic and to read this as a generative process, that it's saying, draw the parameter sigma from this distribution, randomly draw this parameter from that distribution, and then randomly draw y from this distribution, and then sort of fit it to the observed data. And if you remember in the slides yesterday I had about the 2 coins, that's exactly what we were doing. You would simulate the 2 coins and then condition based on whether both were heads or whatever it was. But actually, in Stan, we can really think about the syntax you saw before, twiddles, as being updates to an implicit imperative variable called target. And the idea is that target builds up, that target builds up is an accumulator that builds up a function that we're computing deterministically. And it's this the log sort of density, the log probability of the data, of the joint distribution of the data and the parameters. And so target starts off set at 0, and we calculate in log space, and this is, if you haven't come across this before, working in log space with the logs of probabilities is simply a way of avoiding numerical instabilities, because the log of a small number is like a sort of big negative number, if you like. So it's much better to deal in log space. And it means in log space, of course, what was a multiplication in ordinary space becomes an addition of the logs of the things you multiply together. And so we're calculating the joint distribution of d and theta. So you want to multiply them all together. So effectively what that becomes in log space is adding them all together. So it means we can treat these those distributed as expressions as just updates to this target variable. And so they end up calculating this function here, which is the joint density of particular values of d and theta. And looking at that in a bit more detail, if you've got this fixed data here, then you maybe, let's just pick, suppose we choose a particular value of mu and sigma, then we run this bit of code here, and then that will calculate what the joint density is. So here we're just starting at 0 and adding in these log densities for these different values, getting a particular number, and then we can calculate that. And that, what I've described there, is effectively what happens in inference. That the MCMC, the Monte Carlo Markov chain algorithm, works by just repeatedly finding candidate values for the parameters by searching a particular space, and then evaluating this joint density function. And so in a bit more detail, we have all these guys here. There's a function that we want to calculate, which is really the posterior, which is the posterior distribution of the parameter given the data. But if you actually look at Bayes' rule in log space, which it looks like that, and it says that the joint distribution is basically proportional to, or is a constant away from the actual posterior. So this is what you get from running the program, but it's actually up to a constant the same as the posterior distribution. So it means that in order to calculate f of theta, it really just amounts to running this program multiple times. And so we can give a formal semantics for Stan as follows, which is just particularly simple, which was satisfying to me, that we don't need particularly complicated maths to give the semantics to Stan. So here is a Stan program in general. We've got these 6 compartments, and they contain gammas and s's. And a gamma is just a type environment, giving the name of a variable together with its type, and it's very similar to the gammas I had earlier. And s is just a simple imperative programming language without any randomness in it. But it does have this special target variable that's used as an accumulator. And so the semantics of Stan is the following, and we assume we've got a big step semantics like this. And so S and S dash, they're stores, like the ones I showed you holding the parameters, that curly D, that was just a store. And big S is a statement. And so we can write this down inductively. And then this is the program that you've got. And so the data is specified by a gamma. There's a transform data block, which is where you want to do some pre-processing on the data before you do any inference. And so it may contain some new variables together with some commands that update them. You declare some parameters. You declare transform parameters that, again, are new variables that are determined by a bit of code that runs and updates them from the values of the parameters. We got the model, it's just a bit of code, and you've got some generated quantities like the variance I showed you, which will declare some generated quantity variables and a bit of code. And then to get the semantics, which is this unnormalized log posterior distribution, the parameters conditioned on the observed data, you just take a statement obtained by concatenating together the 4 statements you've seen. You check that the particular theta and d that you're given are actually well typed. So theta is actually a store for gamma p, which is the parameters there. In other words, that's a store that has a value for it for each of the variables in the parameter block. And the data had better be a store corresponding to gamma d, the guy up there. And then you just evaluate it. You say, okay, we set the target to 0, concatenate together those 2 stores, run the program to get an updated store, and all that matters about it is the value of the target. And so that, in a nutshell, is the semantics of Stan. And I've got a few minutes. Let me keep going. So this is this is a more complicated Stan program, and the thing to notice about it is that because you're forced to put all of the code into these different compartments, we've lost any kind of locality. So down here, you've got alpha and beta that are used as arguments to the model. To defining tau, and they're forced to be placed separately from the model block, and generally that's a problem. So we wanted to have a way to automatically to work at a higher level, and the penny dropped that the different blocks corresponded to different security levels or information flow levels. Like I used to work on security, and I think Andrew Myers was here last week, and he probably told you about information security. So the same thing, astonishingly, maybe, happens in probabilistic programming languages, that we have different levels. And so if you think about it, in security, let me say it here. So in security, you've got public and secret data, high security level and low security, and let's say public and secret. And so public data cannot depend on secret data, but secret data can depend on public data. So you have that asymmetry. Well, the same is true in probabilistic programming. So you have data that is lower in the lattice than model. So model can depend on data, but data can't depend on model. You can't have a value in the data block that depends on a parameter, because the parameters are chosen many times, whereas the data is only during execution of the inference mechanism, whereas the data has to be known to start with. And then at gen quant level, which actually is the same level as the inferred probabilities that we had in tabular when I was doing the deciding whether to take a bet or not. Those derived quantities, they can depend on the lower levels, data and model, but those low levels can't depend on them because they only get computed once those low levels have been completed. So we realized that was what was going on, and I'm running out of time now, so I'll send a link round to the paper. But that's the gist of the idea, that we then developed something called slick Stan, where so that was the point of the observation. That we have a slick Stan where we don't put any levels in, we don't have any compartments, but then we can automatically infer, we can automatically infer levels that, that these guys are at data level, this guy's at model level, this guy's at gen quant level. And then having done that, we can then figure out how to optimize where things go, and then put them into the different compartments. So slick Stan compiles to Stan, but it's a much nicer language to work with. You don't have, basically, you can group together logically related things. And the Stan guys love this, and my student Maria got invited out to Columbia in New York to work with them, and hopefully some version of this will get into the next version of Stan. So she's been invited to be one of the core contributors to the Stan project, which is really cool. So in the paper we have the formal semantics, and we show how the translation from slick Stan to Stan goes, and we prove that the semantics are preserved. And so that was our talk at Popple, which I think is a really nice piece of work. So that was our final slide. So I promised to tell you about the end of tabular, Fabula, and now the semantics of Stan, which I've done. Any questions?
So, from my understanding, like Stan heavily uses Hamiltonian Monte Carlo simulations, right? So, so that means like you can't really deal with discrete variables in Stan. Am I correct?
You are correct.
How do you, if so, like how do you, let's say I want to handle like discrete variables in Stan, how would I deal with that?
Well, so yeah, we picked up this observation as well. So we looked into how do people deal with this. Well, what they do is by hand, they sort of, if you like, they sort of sum out the variables. Stan actually allows you to do quite a lot of imperative coding. So you can do coding tricks where you essentially introduce a discrete variable and then use it to influence how the continuous parameters get, or how the likelihood gets updated. And so that's one thing we're currently looking at with Maria, is to have a way to declare discrete variables, but then have them summed out when you actually do the computation. When you do the computation. I mean, which is one approach. I mean, but there could be others. Another way of thinking about it is that Stan is a pretty nice syntax, and I think getting better with something like slick Stan, and so you could simply give it a different inference engine. So maybe use it as a front end for something like infer.net or some other system that can handle discrete distributions. So I guess I try to be principled about this and think about the language as being separate from the underlying implementation. Although, to be honest, at the moment, you can't derive infer.net from Stan syntax, but it'd be nice if you could.
So how does the slick Stan data flow thing relate to what you were saying before about wanting to make it more compositional and adding in functions?
That's a great question, and we go into that in the paper, but it first of all uses the levels to figure out the compartments that the function is going to produce stuff into, and then we statically expand out function calls in a way not dissimilar actually to the way I described the way tabular does it, in that it kind of takes the body of the function and which is already labeled with the compartments that it's going into, and then puts that code into the other into the different compartments in the Stan program that we're generating. But details are in the paper. All right. Oh, okay.
You mentioned at the beginning today that there's some contentious, whether Stan is Turing complete or not. What are some of the barriers, or what are some of the issues with making it more fully expressive language? And that's, I guess. So what are the limitations in Stan? Things you'd like to do, but you can't.
Well, what the gentleman was saying is one, definitely that there's no. There's no good support for discrete variables. It doesn't have things like first-class values. It'd be nice if there were lambda terms in Stan, so you could do sort of functional programming. They're kind of committed to an imperative way of thinking about the world, but I don't. But in fact, they're not really very imperative at all. So having a more having a sort of more functional style of working, I think, would be beneficial. But that's my personal opinion. I think the general view is it'd be better if they could support discrete variables. Another thing, actually, I've heard is that they would like they appreciate they're conscious that a lot of the time the models they're building are hierarchical regressions of the sort I was talking about in the context of Fabula. So I was delighted recently that someone contacted me, and he'd read from the Stan community, who'd read the regression calculus paper, and said this would be really cool, if you had a more compact notation for regressions in Stan. And so hopefully he will pick up on that. We had a first stab at that with a student a few years ago, but this other person might be having a go at it. And so that I've seen Gelman has given talks about Stan, and one of the things he said is, we keep on doing the same thing with these linear regression models, and there's all this boilerplate we've got to write. So I'm hoping they'll like the regression calculus. Although I should find it's a final. I really should stop. The regression calculus is a nice core calculus, but if you actually write things out in the pure language, they become a little bit unreadable, in my humble opinion. And I invented it. So I think we need to. So I think, I'm being a bit self-critical here. I think we need a better syntax for the regression calculus. In a way, it's too compact. It would be like programming in Haskell with just lambdas and no function definitions or something. So I think we need, there's work to be done there. Okay, I really must stop there. Thanks for your attention.